Hello, so in this video we are going to start looking through some indices questions. But before we get there, we're going to actually revisit some of the things that we were doing in last week's session. And we're going to go back to surds, because I've pulled out a slightly more tricky surds question to have a look at together. So here we have on the screen, a rectangle has a length of 2 plus root 2 centimetres. And we're told that the area of that rectangle is 6 plus root 8 centimetres squared. Can we find the perimeter? So this is how we're going to start. Well, first of all, we're dealing with a rectangle. So I guess it makes sense to physically draw ourselves a rectangle, then we can visualise what's going on here. So here we go, we'll draw ourselves out a nice little rectangle like this. Doesn't need to be anything pretty, just as long as we can kind of help to understand what's going on here. Now we're told that the length of this rectangle is 2 plus root 2 centimetres. Now I don't know what length they're talking about, whether they're talking about the longer length or whether they're talking about the shorter length. So I'm just going to pick one. Okay, I'm just going to pick one. So I'm going to use this bottom one as the 2 plus root 2 centimetres. Okay, so 2 plus root 2 centimetres. Now notice here they've just put it in brackets. That's just because you don't then get confused with the centimetres. Those are just the units. All right. Now we're told that the area of this rectangle is 6 plus root 8 centimetres squared. So the area is 6 plus root 8 centimetres squared. And again, don't be confused by the brackets, they're just to separate it from the units there. Okay. So we need to find the perimeter. Now the perimeter is just simply all of the outside lengths added together. Okay, so in other words, it's this length plus this length plus this length plus this length down here. Okay, now so basically it's what happens if you start at a corner and if you walk all the way around the edge of that shape, how far will you walk? Okay, so it's just basically all of the lengths added together. That's the perimeter. Now, are you happy that because it's a rectangle and because we've said that this side down here is 2 plus root 2 centimetres, it must mean that this length up here is also 2 plus root 2 centimetres. Okay, and also we know, again, because it's a rectangle, that whatever this length is, this length must also be the same. Okay, so in other words, we're halfway to finding the perimeter. Okay, we know this side and we know this side. We just need to find the two remaining green sides, which we don't know yet. Okay, so how can we do this? Well, look, we've been given some information here. We've been told that the area of the rectangle is 6 plus root 8 centimetres squared. Now, the way to think about this is literally to ask yourself, well, if I did know all of these lengths, so if I knew this one, and also all the other two as well, okay, how would I find out the area? Okay, so it's almost like we've been given the answer to the question. You then have to go back and think about how you would work that out given the relevant information. Okay, well, if we knew that, okay, if we knew how to work out the area, we would say it would be this length here multiplied by this length here. Okay, so the area of a rectangle will be base times height. Well, look, we know what the base is. Okay, we know what this length here is, 2 plus root 2 centimetres. So therefore, all that's left to do is to find this height here. Okay, so because I don't know what the value of this is at the moment, I'm going to think right the way back to week 1 when we're looking at algebra. Okay, and when we don't know the length of something, we give it a name. And then we can still work with it and hopefully try and find out what that is. So I'm going to call the height of this x. Okay, I'm going to call the height of this rectangle x. And obviously because that's x, this has got to be x as well over here. Okay, so if I knew both x and also the 2 plus root 2, if I knew the length and I knew the height, okay, in order to find out the area of my rectangle, I would say that would be equal to my base, which is 2 plus root 2, multiplied by my height, which is just going to be x. And you notice that I just write it as next to each other. Don't putting the multiplication symbol in here because I'm working with algebra. Okay, if I multiply a number and a letter with algebra, I don't need to put that multiplication symbol in. All right, okay, now I do actually know what the area is in this case, don't I? I know that the area is 6 plus root 8 centimetres squared. So in other words, I'm saying that 6 plus root 8, okay, that's my area, must be equal to my 2 plus root 2 times by x, okay, times by x, right? So think what I'm after. What am I after? Well, in order to find the perimeter, we just said, I need to know what these two sides are here. In other words, I need to know the value of x. So look at this equation that I formed down here. How could I find the value of x? Well, just have a think. Okay, so this is again feeding back into what we were doing last week. If I want to solve this equation here, okay, at the moment, the thing which I want to find is here on the right-hand side. And it's being multiplied with this 2 plus root 2. Okay, so therefore, in order to find the value of x, I need to get that x on its own. I need to make x the subject of the formula. I need to undo this multiplication symbol in here. Okay, so you're happy? I have 2 plus root 2 and I'm multiplying it with x. So in order to undo that, in order to get x on its own, I need to divide by that 2 plus root 2. Okay, so I need to divide both sides by 2 plus root 2. Okay, well, clearly, if I divide the right-hand side, so this side here, by 2 plus root 2, then effectively I'm just going to be left with x. Okay, that's what I wanted. That's the reason why I divided by 2 plus root 2. However, on the left-hand side, I'm going to get 6 plus root 8 divided by 2 plus root 2. Now, I could write it as 6 plus root 8, then divide symbol, 2 plus root 2. But in this case, I'm going to write it as a fraction, okay, because I think it will look slightly neater. So I'm just going to put my 2 plus root 2 on the denominator. You happy that fraction literally just means divide? It means 6 plus root 8 divided by 2 plus root 2. All right. Now, I'm just going to swap the sides over. So I've got x on the left-hand side and 6 plus root 8 on the right-hand side. Doesn't matter, but I think it just looks slightly easier and looks slightly easier to solve if you get it written like this. Okay, so hopefully you're looking at this bit here then. Okay, so hopefully you're looking at this bit here and you're thinking, what can I do with this? How can I find the value of x? Because at the moment, I'm literally saying x is equal to whatever's over here on the right-hand side, okay? Now that is just a number, okay? It's not very nicely written, but that is just a number. If you stick 6 plus root 8 divided by 2 plus root 2 on your calculator, that is just a number. So theoretically, I guess we have finished, except you wouldn't get all the full marks in the exam if you left your answer like this. Okay, because at the moment the thing on the right hand side does not look in its simplest form. Okay, remember we talked quite a lot about simplifying in the first 2 videos. So we need to simplify here. Now, if you remember, okay, in fact we look at an example just like this at the end of the last video, at the end of last week's lesson. This we need to simplify. We need to make the rational denominator. We need to rationalize the denominator, right? So we looked at an example just like this. We were given something that looked just like this, a surd on the top, surd on the bottom. If we wanted to simplify, we simply need to rationalize the denominator. In other words, we need to get rid of any square roots which aren't nice whole numbers on the denominator. Okay, so rationalize the denominator. Okay, so hopefully you're looking at this and you're thinking, I know how to rationalize this. Okay, I know how to rationalize this. What do you need to do? We need to multiply by the conjugate of the denominator. So have a look at what's on the denominator at the moment. It's 2 plus root 2. Now, if you remember the conjugate is just changing that plus to a minus. Okay, so 2 minus root 2 would be the conjugate of 2 plus root 2. But of course, I can't just multiply by 2 minus root 2 just on the denominator, right? I've also got to multiply by it on the numerator as well. Now, I wonder if you can remember why we have to do that? Well, the reason is because then we just get the same numerator, same denominator. It means we're just multiplying by 1. It means that we're not actually changing the value of this at all. Because whenever you see a fraction with the same numerator, same denominator, it's just the same as multiplying by 1. And anything multiplied by 1 is just itself. Okay, so let's actually multiply this out and see what we get here then. So we end up with, on the numerator, 6 plus root 8 times by my 2 minus root 2. Okay, so that's just simply multiplying this with this. All right. Now, on the denominator, hopefully you're starting to see the pattern. So once you do more practice with these, you start to do these very quickly in your head. It's just a difference of 2 squares. Which means that when I multiply this out, anything with a root 2 in will just be completely cancelled. I'd end up with plus 2 root 2, then a minus 2 root 2. Now, if you're not sure what I'm talking about there, then literally have a go at multiplying 2 plus root 2 times by 2 minus root 2. Okay, just simply multiply it out as an ordinary quadratic and you'll simplify it. However, hopefully you've done enough examples with this that you'll be able to use the shortcut, which is just noticing that because you have the conjugates being multiplied together, you should just be left with this times by this and this times by this. Okay, so you should be left with the 2 multiplied by the 2. So on the denominator, you should be left with the 2 multiplied by the 2, which is the 4. And the root 2 times the root 2, which is 2. And then there's a minus in the middle. Okay, so if you've done enough examples of this, you'll be able to confidently do this very quickly. If you haven't, or if you're not quite sure where that comes from, you're not confident enough to do that yet, that's fine. Just multiply those 2 brackets out ordinarily, but you'll get the same answer. Okay, now let's multiply the numerators together. Okay, so all right, we have 6 times by 2, which is 12. And then we have the 6 multiplied by the negative root 2, which is negative 6 root 2. Okay, all right, now let's multiply the root 8 stuff together. So remember, everything with root 8 has to multiply by everything in the second bracket. So positive root 8 multiplied by positive 2 will give you positive 2 root 8. Okay, and then finally this root 8 has to meet up with this negative root 2. So positive root 8 multiplied by negative root 2, that becomes negative. We just end up with the root 8 times the root 2. That means I can multiply the 2 things underneath the square roots together because they're both square roots. So I end up with root of 8 times 2, which is root 16. Okay, like so. So let's just tidy this up ever so slightly. Okay, well, let's have a look. Okay, on the denominator, it's nice and easy. I just end up with 2 because 4 take away 2 is 2. Okay, but on the numerator, let's see what I get. Well, all right, I guess we can simplify this root 8. Okay, have a look. Can you think about how to simplify this root 8 for me? Okay, so remember, I'm looking for 2 numbers which multiply together to make 8, and one of those numbers has to be square. Okay, so root 8 is equal to, well, let's think. 4 times 2 works, doesn't it? So I can break this up into root 4 times root 2, which means that root 4 is 2 times by root 2. Okay, so in other words, I get 12, take away 6 root 2. This thing here becomes 2 times by 2 times by root 2, which is 4 times root 2. Then finally, this root 16 here, well, what's the square root of 16? It's just 4, okay? So therefore I'm taking away 4 here. All right, let's just break it down ever so slightly again. So we end up with 12 take away 4, which is 8. Then negative 6 root 2 plus 4 root 2, which is negative 2 root 2. Then denominator, I just get my 2. Okay, so you see how I've collected those together? I've done the 12, take away the 4 first of all, that gives me the 8. And then I've done the negative 6 root 2 plus 4 root 2. Negative 6 of something plus 4 of something makes negative 2 of that something. Okay, and then over 2 again. And I think we can take it one step further. Just remember this over 2 business just means that both this 8 is over 2 and this 2 root 2 is over 2 as well. Okay, so what's 8 divided by 2? That's 4. And what's negative 2 root 2 divided by 2? Well, can you see that the 2 divided by 2 just effectively cancel to make 1? So therefore I'm just going to be left with negative root 2. And that there would be my final answer for, well, what was that again? That was x. Okay, that was x. So if I come right up to my diagram up the top here, I now know that x is 4 minus root 2. That's what I've just found. So x is 4 minus root 2. So I'm going to rewrite that instead of x now. 4 minus root 2. And I also know that this x here is also 4 minus root 2. Okay, so it now means that if I basically copy all of this down to the bottom, we can do a little bit more work with it. Okay, so there we go. So basically now I know all of the lengths of my rectangle. So just remember, what was the original question? Well, the original question was, can you find the perimeter of this shape? So just remember, the perimeter is just all of the outside lengths added together. So therefore, I just need to add all of these lengths together. Okay, so there you go. So if I need to add all these lengths together, I get 2 plus root 2 plus 4 minus root 2 plus 2 plus root 2 plus 4 minus root 2, and see what I get. So I've literally just added all of these 4 lengths of my rectangle together. So let's see. Well, actually, I've written in brackets so that you can see what I'm talking about. So each length of my rectangle is separated by a bracket. But you're happy I don't really need these brackets. I'm just going to get rid of them. Okay, they're just used there as a kind of mental separator for you to see where I'm getting these numbers from. Okay, so let's actually go through this. Let's collect together, first of all of the numbers. Okay, so we've got a 2, a 4, a 2, and a 4. I need to add all those together. So 2 plus 4 plus 2 plus 4 is going to be, what's that going to be? 2 plus 4 is 6, then plus another 2 is 8, plus another 4, that's 12. Okay, so it's going to be 12. Then we've got loads of root 2's which I need to think about. Well, have a look. I have root 2. Let me get rid of those red markings. I have root 2, then I take away a root 2. So in total I've got nothing so far. But then I add on another root 2, well that's root 2. Then if I take away another root 2, that's going to give me 0. So actually the final perimeter of my shape should just be 12. Okay, so the perimeter of my shape should be 12. Make sure you put the units in. So in this case we're talking about centimetres. How do I know it's centimetres? Well, because all of my lengths and also the area of my shape were also given in centimetres as well. Okay, so the perimeter of my shape here should be 12 centimetres. Okay, so hopefully that makes sense. Okay, so let's make a start on the next little section which we want to go through today, which is going to be indices. Now, there's different words for indices, okay, and I'll write them down here. Okay, so an indices basically is the plural of an index. So what do I mean by that? Okay, well, let me show you with a sort of a thought experiment. Okay, so I want you to think about this. If I had 2 plus 2 plus 2, okay, so 2 plus 2 plus 2, okay. Now, we have shorthand notation for this situation. So basically what I'm doing here is adding a number to itself 3 times. So I'm literally taking 2 and then I'm adding it to itself in total of 3 times. Okay, so 2 plus 2 plus 2. So another way that I could write this is 3 times 2. What this literally means is 2 3 times. Okay, 2 3 times. So in other words, multiplication is literally when I'm adding a number to itself multiple times. Okay, it's repeated addition. Okay, so multiplication is repeated addition. Now in the same fashion, we also have notation for something like this. So if I had not 2 plus 2 plus 2, but 2 times 2 times 2. Okay, so in other words, in this case, instead of adding 2 to itself 3 times, I'm multiplying 2 by itself 3 times. Okay, well, fortunately, we also have notation for these situations as well. Okay, and it's this. So this time we still have the 2 to represent that's the thing that we're multiplying in this case. Okay, but in this case, we need to represent the fact that we're multiplying 2 by itself 3 times. So therefore, I'm going to put the 3 up here instead. Okay, and this literally means repeated multiplication. Okay, so it's really important to be aware of the different notations here. So repeated multiplication. Okay, so it's literally what happens. Okay, it's literally what happens when you multiply a number by itself. So when you're adding a number to itself, you multiply it. Okay, so you've got this notation here. All right, but when you're multiplying a number by itself, you use this notation here instead. Okay, so we're going to play around with this notation. So let me just write that down again. So we have 2 to the power 3. Now let's just think, what is 2 to the power 3? Well, it means 2 times 2 times 2, remember? So 2 multiplied by itself 3 times. Well, 2 times 2 is 4. Times it with another 2, that makes 8. So in other words, the answer to this would be 8. Now what I've written down here is basically a really important thing. And this is what we're going to be focusing on today. And we actually give a name to each of the different things in this equation here. Okay, so the 2, just remember that the 2 is the thing that we're multiplying by itself. Okay, so in this case, we're multiplying the 2 by itself 3 times. So if I write something like this down, so 2 to the power 3 equals 8. Okay, the base down here, we would call the base. Okay, so the 2 in this case, we would call the base. That is the number that we are multiplying by itself however many times. Then how many times we're multiplying itself, multiplying the 2 by itself, we call that either the power or the index. In fact, there is another word for it, which is the exponent. Okay, so you may have come across these words before. They all mean the same. Okay, so the base is the number that we're multiplying by itself, and the power is the number of times that we're multiplying that base by itself. So in this case, 3. And we call that the power or the index or the exponent. Now, by the way, okay, if we have more than one power, if we have more than one index, okay, we call it an indices, okay, so that's the plural, or powers, okay, or exponents, okay. So indices, this word up here, is just simply the plural of index, okay. So index is the singular, it's when you've just got one, and indices is when you've got more than one, okay. Now this number over here, we actually just call a number. Now, some people Okay, now some people, it depends on how you look at this, but some people say that actually this could be thought of as the power, because if you think about it, it's the result of raising that 2 to the power of 3. Okay, but in this case, just to avoid confusion, I want you to think that the 2 is the base, that's the thing that you're multiplying by itself. The 3 is the power, the index or the exponent, don't care what you call it, okay? And that's the number of times that you're multiplying the 2 by itself. Then the result of that is just simply the number, the numeral, okay? All right, fine. So let's actually have a look at some examples then. So if I gave you 3 to the power 4, okay, well, hopefully you would tell me that this is 3 times 3 times 3 times 3. That's literally what I want you to think in your head. 3 to the power 4 means 3 multiplied by itself 4 times, okay? Remember that the base tells you what you're multiplying and the power tells you how many times you're multiplying it, okay? So in this case, 3 to the power 4 should be 81, okay? If I gave you 7 to the power of 2, okay, 7 to the power of 2, that means that you take the 7, because the base is 7, and you multiply it by itself 2 times, because that is the power or the index. That tells you how many times you're multiplying by itself. So in this case, this should be 49. Okay, so basically an index or a power is all about trying to make multiplication written in an easier way. So when you have repeated multiplication, it's all about writing that in a more streamlined and easier way to follow. Okay, now what we're going to start looking at in this video is the laws of indices. Now, actually, I hate this title, okay? Otherwise, sort of you can abbreviate it to index laws if you like. But I actually take real objection to the fact that it says laws there, because you know, as well as I do, that a law simply means you have to follow it. Okay, otherwise everything will kind of go wrong. Okay, so a law means that you have to follow it, and this is not the case. Okay, if you don't follow a law, it generally means that you're doing something wrong. But I hate the word law because it kind of just means that you're doing something wrong if you don't follow it. Right? What I prefer to call this is shortcuts, because that's literally what they are. Okay, so what I mean by laws is that they're actually just little shortcuts, okay? And it kind of comes back to when we were looking at algebra, right? When we notice a pattern in maths, we try and generalize it so that it's easy to follow in sort of general cases, okay? Same kind of thing going on here. So let me show you what I mean, right? The first sort of observation that I want you to make is something like this. If I have 3 to the power of 2, and I multiply it with 3 to the power of 5. Okay, so notice in this case, the bases are the same. Okay, so the 3 is the same. That's the thing that we're multiplying together. Okay, so the bases are the same. I want to notice, or I want to observe something so that I can generalize it to other cases as well. Okay, so let's first of all just start out by writing what 3 to the power of 2 is. Okay, so 3 to the power of 2 will just be 3 multiplied by 3. It's just 3 multiplied by itself 2 times. Okay, now so I'm multiplying that. Now if I have a think about what 3 to the power 5 is. Well, 3 to the power 5 is just 3 multiplied by itself 5 times. All right, so my question is, how many times are you multiplying 3 by itself? How many times are you multiplying 3 by itself? Well, let's have a look. You were multiplying 3 by itself twice because you had 3 to the power of 2 here. And then you multiplied 3 by itself another 5 times, because that's where the 3 to the power of 5 told you to do. Okay, so in total, you were multiplying by itself 2 times, then you multiplied another 5 times, so in total, you're multiplying itself, 3 by itself, 7 times. Now just think, where did that 7 come from? It came from the fact that you started off with the 2 times that you're multiplying 3 by itself, and then you multiplied 3 by itself another 5 times, which gave you 7 times in total. You just simply added those 2 powers together, okay? So in other words, in general, if I have some base, and I'm going to call it b for base, okay? And if I raise it to some power, let's say n, and if I have the same base, so same b, and if I multiply it to another power, I'm just going to call it m. If I want to simplify this, if I want to use a shortcut here, rather than writing it out in full and then kind of collapsing it down to here, what I'm just going to realize is I just need to add those powers together. So I keep the base the same, but then I add the powers together. Okay, so let me give you an example here. Let me give you an example. Let's suppose I have 4 to the power of 5 and I multiply that by 4 to the power of 7. Okay, so 4 to the power of 5 multiplied by 4 to the power of 7. Well, how many times should I be multiplying 4 by itself? Well, I have 5 times here, 7 times here. This law just tells me that I should add those powers together. So I should multiply 4 to the power of 5 plus 7 times, which is 13. Okay, so 4 to the power of 5 times by 4 to the power of 7, I can shortcut that down to 4 to the power of 13. So you notice this is all about shortcuts, right? I've noticed what's going on here. I've realized what's going on. I just simply need to add the two powers together if I'm multiplying in the bases, okay? Which means that I can shortcut this and I don't have to write out 4 times 4 times 4 times 4 times 4 for 4 to the power of 5 and then 4 multiplied by itself 7 times. I just realize I should add the powers together. Another example. Let's suppose I have 8 to the power of 6 multiplied by 8 to the power of 100. Now can you see here, it doesn't make sense to write out 8 multiplied by itself 100 times because I realise in this example that it should just be 8 to the power of 106. Now, you notice that this only works if the bases are the same. Just remember, the bases are the numbers down here. So the bases have to be the same, right? The bases have to be the same. Otherwise, it won't work. For example, if I take 3 to the power of 8 and I multiply it with 5 to the power of 2, okay? That would not be equal to, well, 8 plus 2 is 10, so that should be the power. But then what do you do in the bases, okay? So it wouldn't be, for example, 15 to the power of 10. That wouldn't work, okay? That wouldn't work. So you don't just multiply the bases together, okay? So that's a really important thing. The bases must be the same. If the bases are different, you can't do it. Well, I say you can't do it. I think there's one example when you can. For example, something like this. 2 to the power of 5 multiplied by 4 to the power of 3. Okay, now just have a think here, just have a think. You notice in this case the bases are different. You have the 2 and the 4. And based on the previous example I've just given you, you'll be like, I can't do this, can I? But I think you can. And here's why. Because you realise, hopefully you realise, that 4 is just 2 to the power of 2. So in other words, I can turn this into something with the same base. Okay, have a look. If I say 2 to the power of 5 is just the same, so 2 to the power of 5 times by, instead of saying 4 to the power of 3, I'm going to say 2 to the power of 2, all raised to the power of 3. Okay, and if I then expand this out, I'll have 2 to the power of 5 multiplied by, well, 2 to the power of 2 raised to the power of 3 is just going to be 2 to the power of 2 times by 2 to the power of 2 times by 2 to the power of 2. You happy? I've just literally multiplied 2 to the power of 2 by itself 3 times. That's literally all that says. Okay, so in total, I should just add all these powers together. So 2 to the power of 5 times by 2 to the power of 2 times by 2 to the power of 2 times by 2 to the power of 2, right? Just need to add all the powers together, and it's going to give me 2 to the power of 5 plus 2 plus 2 plus 2. That's going to give me 2 to the power of 11. Okay, so just be aware. In general, if you have different bases, you can't use this shortcut, except if you notice that the base can be written as one of the other bases raised to a power. Okay, so in this case, because I realised that 4 was just 2 to the power of 2, then I had the same base being multiplied together, then I could use this shortcut. All right, fine. Let's have a look at another sort of thing which we can observe. Let's have a look at, for example, 3 to the power of 8 divided by 3 to the power of 2. Now in this case, I'm going to write my division in a slightly different way. I'm going to write it as a fraction. So I'm going to write it as 3 to the power of 8 over 3 to the power of 2. Okay, well let's actually just write out what 3 to the power of 8 looks like. So 3 to the power of 8 should just be 3 times 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 3. In other words, 3 multiplied by itself 8 times. And on the denominator, I should have just 3 multiplied by itself 2 times. Now have a look. In this case, because I'm multiplying loads of stuff together on the numerator and I'm multiplying stuff with the same base together on the denominator, I should do a bit of cancellation. So have a look. This 3 cancels with this 3. So in total, I've cancelled 1 3 off, okay, on the numerator and denominator. And look, this 3 also cancels with this 3. So in other words, I've cancelled 2 things off on the numerator and denominator, which means that on the numerator, I started out with 8 things, okay? And you saw that from up here. I started out with 8 things on the numerator, but then I came along and I cancelled off 2 things because there were 2 3s on the denominator, okay? So if I start off with 8 things and I'm left with 2 less, that means that I'll be left with 3 to the power of 6. Okay, so in this case, I should just subtract these powers together. Okay, you notice if I just look at this, 3 to the power of 8 divided by 3 to the power of 2, I should just subtract those powers to give me my 3 to the power of 6. Okay, reason? Because I'm literally cancelling stuff off. All right, so in other words, if I generalize this, b to the power of n divided by b to the power of m should just be b to the power of n minus m. Okay, so as an example, if we have like 4 to the power of 8 divided by 4 to the power of 5, what should I do to these powers? I should just subtract them. So I keep the base the same, the 4 is the same, but then 8 minus 5, that gives me 3. Okay, and similar as before, okay, similar kind of pattern as before, you need to make sure you have the same base, unless you can write that base as a power of the other base, okay, like we did with this example here. All right, now you notice that so far that's quite nice. Okay, so the first law that we notice is that if you're multiplying the two things together in the base, you should add in the powers. Okay, you should add in the powers. Now we've just noticed that if you're dividing in the base, that means that you should subtract in the powers. There's a nice kind of reciprocity going on there, okay? There's a nice converse going on there, okay? So now let's have a look at another theorem, or another kind of shortcut that we can see. Let's take, for example, 3 to the power of 3. Let's actually change that to a different power. Let's change it to 3 to the power of 4. And we're going to raise this to the power of 5, okay? It's going to raise this to the power of 5. Let's have a look. Okay, 3 to the power of 4 raised to the power of 5. Now, all this means is take whatever's down here, at the moment 3 to the power of 4 is my base, and multiply by itself 5 times. Okay, so we'll have 3 to the power of 4, multiplied by 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 3 to the power of 4. So I'm literally just treating 3 to the power of 4 as my base here. And then I'm just doing that and multiplying by itself 5 times. Okay. Well, I've just seen in the last kind of rules that if I have the same base being multiplied together, I should just add the powers. So in this case, I just should add the 4s together. Well, how many 4s am I adding together? I'm adding 5 of them together. So this is just like repeated addition. In other words, I can treat this as multiplication. So because I have 4 and I'm adding it to itself 5 times, I can treat this as 4 times by 5. Okay, because I have 4 5 times. Okay, which will be 3 to the power of 20. So in other words, when I get treated with an example like this, when I have a base raised to a power, then I'm raising that entire thing to a power, I should just multiply the powers together. Have a look. 4 times 5 gives me 20. All right. So in general, if I have b to the power of n and I raise it to a different power, let's say m, could be the same power, doesn't matter, then this will be b to the power of n times by m. Okay, so that's your kind of third law which you need to observe. So as an example, if I give you 6 to the power of 3, all raised to the power of 5, well, this law tells me that I should just multiply those powers together. So 6 stays the same, and I'm going to get 3 times 5, which is 15. Take another example. Let's take 10 to the power of 8, all raised to the power of 5. That's going to give me, in fact, let's use a different power. Let's use 9, okay? 10 to the power of 8, all raised to the power of 9. Well, what's 8 times 9? That's 72. So I'll get 10 to the power of 72, okay? It even works with situations like this, okay? If I have 2x, all raised to the power of 4, okay? Well, in this case, what I'm going to need to do is raise both of these things inside the brackets to the power of 4. So I need to raise the 2 to the power of 4, and I need to raise the x to the power of 4. Okay, so 2 to the power of 4 and then the x to the power of 4, which is going to give me, well, 2 to the power of 4 is 16 and x to the power of 4 is x to the power of 4. Okay, another example, one of those, let's take, for example, 3 to the power of x. Let's use a different letter. Let's use y squared, all raised to the power of 3. So let's have a look at this. Well, I need to raise the 3 to the power of 3 and I need to raise the y squared to the power of 3. Okay. So 3 to the power of 3 is 27. Y squared to the power of 3, well, I just multiply those two powers together. That's going to give me y to the power of 6. Okay, does that make sense? Hopefully it does. All right, so let's have a look at another kind of shortcut that we can observe. Okay, let's try something like this. If I took 3 to the power of 1, Now let's think, could I do anything with this? Well, what 3 to the power of 1 means is just simply taking 3 and just multiplying by itself once. So in other words, it's just going to be 3, okay? Just like if I had 3 to the power of 2, well actually let's do 3 to the power of 3 first of all. So 3 to the power of 3 would mean 3 multiplied by itself 3 times. If I looked at 3 to the power of 2, it would mean 3 multiplied by itself twice, which means that 3 to the power of 1 should just mean, well, there's just 1 3 sitting there. Okay, so in other words, if I generalize this, any number to the power of 1 should just be itself. Okay, I can just write that as itself. So as an example, if I had 10 to the power of 1, that should just be 10. If I had, I don't know, 15 to the power of 1, that's just going to be 15. If I had 1,000 to the power of 1, that's just going to be 1,000. Right? So any number to the power of 1 will just be itself. That's nice and easy, okay? Again, this is all about just observing shortcuts. Once I notice a pattern, it just means that I can generalize. Okay, so let's keep going then. Let's see the next law. Let's look at number 5, okay? Well, okay, what about 3 to the power of 0 then? 3 to the power of 0. Now, some people think, well, is that just 3? Is that just 3? Well, it can't be 3 because we've just seen in the last example that if I have any number raised to the power of 1, that's just itself. Okay, so I think what we need to do is actually continue this pattern which we've observed here. Okay, so if I just bring it down here now. So we've just noticed that if we have 3 to the power of 3, okay, if we just had 3 to the power of 3, that's 3 multiplied by itself 3 times. 3 to the power of 2 should be 3 multiplied by itself twice. 3 to the power of 1 is just 3. So the next one on the list is just 3 to the power of 0. So what I need to do is kind of think about what's happening here. So every single time I decrease my power, okay, so from 3 to the 3, to 3 to the 2, to 3 to the 1, to 3 to the power of 0, I'm decreasing the power by 1, which means on the right hand side, all I'm effectively doing is dividing by 3. You happy? Because you notice that on the right hand side, I'm just dropping a multiplied by 3. So in other words, to get rid of a multiplied by 3, I need to divide by 3. So if I just keep the pattern going, if I go from 3 to the power of 1 equals 3, if I want to get to 3 to the power of 0, I should divide that number by 3. So in other words, what is 3 divided by 3? Well, it's just 1. It's just 1, right? So in other words, 3 to the power of 0 should just be 1. Okay, and this is true of any power. So any power to the power of 0 is always going to just be 1. Okay, it's not 0, it is 1. So any number to the power of 0 is 1. So as an example, if I give you 5 to the power of 0, guess what? That's 1. If I give you 1,000 to the power of 0, guess what? That's 1. Okay, so any base to the power of 0 should always be 1 because of this pattern that we observe over here, because you're effectively just dividing by 3. Now you notice kind of where we're going from here. We've just looked at 3 to the power of 1. That's just itself. 3 to the power of 0, that's 1. What about 3 to a negative number? Like surely we should just be able to keep this pattern going, right? So for example, my next question is, what would 3 to the power of negative 2 be? What would 3 to the power of negative 2 be? All right, well, let's have a look at this. So let's bring my pattern down. So here we go. And I've just noticed that every single time I decrease the power by 1, I should divide by 3. So we've just done 3 to the power of 0. That gives us 1. Okay, so let's just keep this pattern going. All right, let's just keep this pattern going. So the next one down would be 3 to the negative 1. Okay, 3 to the negative 1. So if I take 1 and I divide it by 3, that should give me, well, guess what? 1/3. Okay, 1 divided by 3. Okay, in actual fact, let me just rewrite these top two. Okay, so 3 to the power of 3 is going to be 27. 3 to the power of 2 is going to be 9. It might be easier to spot it that way. All right. Now, if I do 3 to the power of negative 2, which is the one that I want, that should just be, well, I take the previous one and I divide it by another 3. Okay, so 1/3 divided by 3, that's going to give me a 9th. Okay, so in other words, this thing here should be 1/9. Now, how did I know it was a 9th? How did I see it was a 9th? Well, let's actually have a look at this list that I've written over here. Okay, do you notice that the 3 to the power of 0 is just 1? Let's actually start off there. That's kind of the balance point. Okay, but then do you see 3 to the power of 1 and 3 to the power of negative 1 have a relationship between them? Okay, so 3 to the power of 1 is 3 and 3 to the power of negative 1 is 1/3. Okay, if I notice the next one, okay, so do you notice a relationship between 3 to the power of 2 and 3 to the power of negative 2? So 3 to the power of 2 is 9, 3 to the power of negative 2 is 1 over 9. Okay? So using this pattern, I wonder if you could tell me what 3 to the power of negative 3 is. Well, it's got to have a relationship with 3 to the power of 3. Are you happy? So you notice that 3 to the power of negative 3 should just be 1 over whatever 3 to the power of 3 is, which in this case is 1 over 27. Okay? So in other words, we can generalize this, that any base to a negative power should just be the reciprocal, just remember reciprocal means 1 over, whatever that base is to a positive power. Okay, so b to the power of negative n should be 1 over whatever b is to the positive n. Okay, and you notice because we're doing this pattern here, okay, this pattern will always hold. Okay, so as an example, if I asked you for 5 to the negative 2, okay, well you should be able to tell me that should just be 1 over whatever 5 to the power of 2 is, which should just be 1 over 25. Okay, if I asked you for 6 to the power of negative 1, well that should just be 1 over whatever 6 is to the power of positive 1, which is just 1 over 6. Okay, if I asked you for 2 to the power of negative 5, well that should just be 1 over 2 whatever 1 over 2 to the power of whatever positive 5 is. So that's 1 over 32. Okay. Now this will also work with any fractions. If you just think all I'm doing here, this 1 over business just simply means reciprocal. Just simply means flip it upside down. So if I take a fraction, okay, if I take something like 2/3 and raise it to the power of negative 2, let's think about that. Okay, well I have just literally said that whenever you raise a base to a negative power, like we were doing up here, you just simply do the reciprocal. You just simply flip the fraction upside down. So you make it 1 over. Okay, so let's do the same thing here. Let's flip the fraction upside down, so 3 over 2, and raise it to the power of positive 2. So you raise it to the positive power. Okay? So actually, if I just square this, all this fraction squared literally means is square the top, square the bottom. So 3 squared over 2 squared. Okay, or 9 over 4 if you prefer. Okay? As another example, let's suppose we have 8/5 to the power of, let's say, negative 1. Okay? Well, that's going to be 5 over 8 raised to the power of positive 1. Or just 5 to the power of 1 over 8 to the power of 1. So the power gets distributed over the numerator and denominator. Or we can just simply write that as 5/8. Okay? Any others? Well, all right, let's try 5 over 2 raised to negative 3. Well, this just simply mean flip the fraction, so 2 over 5, raise it to the positive power. And of course, a fraction raised to power, we just put that power on the numerator and put the power on the denominator. So 2 to the power of 3 is 8, 5 to the power of 3 is 125. Okay, so hopefully that makes sense. Okay, raising something to the negative power, don't get scared of it. It just simply means flip it upside down, raise it to the positive power. All right, let's keep going. So I think we're on to number 6 now. We're on to number 6. So number 6, I'm actually going to split into 2 parts. Okay, so I'm going to call this one 6a. And you'll see why I'm doing this in just a second, because we're going to look at a simpler case first, and then we'll extend it in part B to a more complex case and put it all together. Okay, so first of all, what I'm going to do is I'm going to give you what is 3 to the power of 1/2. Okay, so I'm going to ask you, what is 3 to the power of 1/2? Now, in order to get this to work, okay, I'm actually just going to first of all let this equal to a letter. Okay, so you notice that I'm using my traditional trick here. I'm using my traditional trick, which is if I don't know what the value of something is at the moment, so 3 to the power of 1/2, don't know what that is at the moment. All right, I'm just going to give it a letter. I'm going to give it a name. Then I can work with it and see what I can do. So what I'm first of all going to do is I'm going to try and get rid of this power of 1/2. Well, are you happy that if I square both sides of the equation, okay, on the left-hand side, what should I be left with? Well, you notice this is just using law 3, okay? If I have 3 raised to some power, then I'm raising the entire thing to another power. I should just multiply the powers together. So in other words, what's half of 2? Well, half of 2 is just 1. So on the left-hand side, I just get 3 to the power of 1. On the right-hand side, I just get x squared. All right? So 3 to the power of 1, well, I've just seen that's just 3. And x squared, that should just be, well, x squared. Okay? Now, if I just flip the sides around, I get x squared equals 3, which means, remember, right at the very start, what did I want to find? I wanted to find out what x was. I wanted to find out what this 3 to the power of a half could be rewritten as, okay? So if you see here, I'm going to be a little bit naughty here. In order to get rid of a squaring, what do you do? Well, you do a square rooting. We saw that in the last video, okay? So if I square root this, I get the square root of 3. Now, strictly speaking, I should put plus or minus, but I'm not in this case. I'm not going to put plus or minus in this case because I just wanted you to notice the pattern, okay? So in other words, the thing which I started with, which was 3 to the power of a half, that was my x, is now equal to the square root of 3, okay? So therefore, 3 to the power of a half should be equal to the square root of 3, okay? Now, do you notice any relationships between the power and what's going on over here on the right hand side? Okay, so I've got power of half, then I'm taking the square root. Okay, so the same base is there. I can still see the 3 here and still see the 3 here. Okay, well, basically, in general, if I have some base, and I raise it to a fractional power, so for example 1 over n, okay, that should be equal to the nth root of that base. Should be equal to the nth root of that base, because I can always follow this same logic which I used above. Okay, I can always follow the same logic I used above. So in other words, b raised to some fractional power should be the nth root of b. Okay, so b to the power of 1 over n should be the nth root of b. So as an example, if I asked you for 2 to the power of a quarter, I should be able to write that as, keep the 2 the same, and take now the 4th root. So you notice that this denominator becomes whatever root I'm taking, okay? As another example, if I take 3 to the power of 1/8, that should be equal to, you guessed it, the 8th root of 3. Again, that denominator becomes the root, all right? See another example, 5 to the power of a 7th. Well, I keep the 5 the same, and I take, you guessed it, the 7th root. Okay, so the denominator of my fraction climbs down to become a root, and you've seen why, because you should always be able to follow this kind of reasoning just with different numbers, okay, to prove that this is always going to be the case. Now that's 6a, okay, I'm going to move very swiftly onto 6b, because you notice 6a is all about what happens if there's a 1 on the numerator of this fraction. So 6b is going to be what happens if there's not a 1 on the fraction, the power of the on the numerator of my fraction. So if I take, for example, 3 to the power of 2/3, okay, 3 to the power of 2/3. Well, you've just seen that if this was 3 to the power of 1/3, this should be equal to the cubed root of 3. This should be equal to the cubed root of 3, okay? So what I need to do is make this fraction look as if it's just got a 1 on the numerator, because I know how to deal with that. I deal with it over here, okay? So how could I do that? Well, are you happy that 2/3 can be written as 2 times by a third? Okay, so 2/3 is just literally 2 lots of 1/3. Okay, now I've just seen that if I use my third law of indices in reverse, would you be happy that I know a law of indices which happens when I multiply the 2 powers together? It would simply be this: 3 to the power of 2 all raised to the power of a third. Look, are you happy? If I multiply those two things together, I would get the same thing. Okay, so when I have 3 to the power of 2, all raised to the power of a third, I should just multiply those two fractions together, or those two powers together, rather. So now it's just literally the same. Okay, now instead of having 3 to the power of 2/3, I've got 3 to the power of 2 raised to the power of 1/3, because I know what happens when I have the base, when I have a fraction with 1 on the numerator. Okay, the power just simply climbs down to become a base, to become a root. So it'll be 3 to the power of 2, and then you take the cube root of that. Okay, so in general, b to the power of n over m, that should be equal to the m climbs down to become a root, and the b climbs up to become a power. Now you notice in this case it doesn't really matter what order I do it in. So I can either do it in that order, so take b to the power of n and then take the mth root, or I could take the mth root first and then raise all of that to the power of n. It doesn't matter what order I do it in. Okay, because you notice that I could have equally written this round the other way. Okay, I could have equally written this as 3 to the power of a third, all raised to the power of 2. Okay, so 3 to the power of a third I know is the cube root of 3, and if I raise all of that to the power of 2. So it doesn't matter what order I do it in. Okay, so it doesn't matter what order I do it in. Let's see it with an example. Okay, so let's try it with 5 to the power of 2/3. Well, okay, the denominator of the fraction always climbs down to become that root. 5 stays the same. It doesn't matter whether I put the 2 here or outside there, but that's what we get. Okay, so the cube root of 5 squared. Okay, or if you prefer, you could write that as the cube root of 25. Doesn't matter which. Okay, see it with another example. Let's try 8 to the power of 5/7. Well, that's just going to be the root, which is 7, then 8 to the power 5. Okay, so you notice it's always the denominator that climbs down to become the root. Okay, just try it with one more example. Let's try it with 7 to the power of 8/10. All right, so 10 climbs down to become a root, 7 stays the same, 8 comes up here. You see how easy that is? Okay, 10 becomes the root, the 8 stays up there. All right, so let's actually have a look for the last sort of 10 minutes or so at some slightly more examples which actually use all of these indices or more than one law of indices at a time. So let's try, for example, simplifying. So remember, I'm using simplifying here again now. Okay, because I want to make this look simpler. All right, let's try 5. Let's try 5 to the power of -2/3. Oh, okay. Well, we've just seen with the last example or the last examples that if you have a negative, so I'm going to focus on the negative first of all because I'm not worried about the fractional power. I know how to deal with that. So let's deal with the negative first of all. The negative just means 1 over, just means flip it upside down. So 1 over 5 to the positive 2/3. Okay, and then if I look at this 5 to the power of 2/3, I can break this down into the cube root, so 1 over still, cube root of 5 to the power of 2. Okay, so that works. What about something like this? What about 8/7 all raised to the power of -8/5? All right, something like that. Well, okay, let's first of all deal with the negative. So the negative means that you should flip it upside down. So take the fraction, flip it upside down, raise it to the positive power, which in this case is 8/5. Okay, then I'm going to basically put the 8/5 on both the numerator and the denominator. Okay, so the 8/5 goes here and the 8/5 goes here as well. Now, what does a power of 8/5 mean? Well, it just simply means the 5th root of that number raised to the power of 8. So 5th root of that power raised to the power of 8. And that'll be fine. Okay, so no matter how complicated it gets, no matter how complicated it looks, just break the laws down in your head and then follow it through logically. All right, let's actually have a look at some solving equations examples now. So let's have a go at solving an equation something like this. So let's try 25 to the power of x equals 5 to the power of 4x plus 1. Okay, so let's have a look at this. Well, have a look. At the moment, we can't really make any simplifications. So at the moment, it's kind of like 25 to some power has got to be equal to 5 raised to some power times 4 plus 1. Okay, you can do it logically, you can kind of think it through, but I think that'd be quite a difficult one to kind of do intuitively. So what I want to do instead is make the left-hand side and the right-hand side look as much like each other as possible. Namely, in this case, I want the bases to be the same, because the majority of the laws of indices that we've just looked at focus on the fact that the bases are pretty much the same. So we want to make the bases look as much the same as possible. Okay, so have a look. You notice this 25, you could write that as 5 squared. Okay, that would literally be the same. So let's do this. So because I can write that 25 as 5 squared, I'll still have it raised to the power of x, and the right hand side I'm just going to keep the same. Now I know a law of indices which will actually simplify this for me, so get rid of the brackets. I just need to multiply the 2 and the x together. So I get 5 to the power of 2x. Then here I get 5 to the power of 4x plus 1. So here now, because I've got the same base, okay, I've got 5 to the power of something equals 5 to the power of something. That's literally how I'm thinking about this. 5 to the power of something must be the same as 5 to the power of something. Well, because I've got 5 to the power of something on both sides, those somethings must be the same, okay? So therefore I know that 2x must be 4x plus 1. That's the only way this equation can work. Because if I have the same base, I've got 5. So 5 to the power of something must be the same as 5 to the power of something. The only way that can be true is if those powers are the same. So in other words, 2x must be the same as 4x plus 1. Then it's just an equation that we're solving. Okay, so if I solve this, we can get all the x's on the same side. So I'm going to take away 2x from both sides. So 0 must be 2x plus 1. Then I'm going to take away 1 from both sides. So I'm going to get 2x equals negative 1, which means that x equals negative 1/2. And that will be the solution of this equation. Okay, so if I start off with 25 to the power of something, must be 5 times 4 times that something plus 1. The answer will be negative 1/2. Okay, let's have a look at another example. Let's try something like, let's see. Yeah, let's try solving 16 to the power of x plus 1 must be equal to 8 to the power of 2x plus 1. Okay, so let's have a look at an example like this. Well, first of all, again, I want the bases to be the same. So at the moment I've got a 16 on this side and I've got an 8 on this side. I want the bases to be the same, and hopefully we can do a similar trick to what we were doing in the last example. So do you notice that 16, if you know your powers of 2, you should be able to recognise that 16 is 2 to the power of 4. Okay, if you weren't sure about that, you could always sit down on a calculator and just try different bases. And let's see, well, 8 is 2 to the power of 3. Okay, so this comes with experience. If you didn't recognise that straight off, you could just try different sort of bases and raise them to different powers and see if they come to 16 or 18, or 16 to 8, excuse me. Or you can just simply do what I do. Once you get experience with these kind of things, know your powers of 2, you recognise 16 and 8 are both 2 to the power of something. Okay, so I'm going to rewrite this. So 16, I'm going to rewrite as 2 to the power of 4. That's all still being raised to x plus 1. Then 8, I'm going to rewrite as 2 to the power of 3, and that's all being raised to 2x plus 1. Okay? All right, fine. Now I'm just going to follow the same technique as before. I should just multiply the two powers together. So 4 multiplied by x plus 1. So let's do that. So we have 2. Then I need 4 times by x plus 1. Now be careful. Do not write that down, because that could be interpreted as 4x plus 1. That's not what I want. I want 4 times by the entirety of x plus 1. And the same thing over here. I have 3 multiplied by the entirety of 2x plus 1. Now, are you happy here that because I have 2 to the power of something, and that must be the same as 2 to the power of something, those somethings must be the same. So in other words, 4 times by x plus 1 must be the same as 3 multiplied by 2x plus 1. Okay? So now all I need to do is just expand this out and solve it. So let's go 4x plus 4. Let's just expand the bracket on the left-hand side, expand the bracket on the right-hand side, we get 6x plus 3. All right, let's simplify this then. Let's take away 4x from both sides. So on the left-hand side I get 4, right-hand side I get 2x plus 3. Let's take away 3 from both sides. So on the left-hand side, well, I'll get 2x, and then on 4 take away 3, which is 1. So I've just swapped those two sides over as well. Then I'm just going to divide by 2, so I get x equals 1/2. Okay, I get x equals 1/2. Does that make sense to everyone? Does that make sense? Okay. It also means that you can solve things like this. Okay. So let's try something like this. Let's suppose we are given that y equals 2 to the power of x. Okay. So y is just whatever 2 to the power of x is. Okay. Can we express the following in terms of y? Okay, so can we express 2 to the power of x plus 2 and 4 to the power of x in terms of y? Now, all that in terms of y bit means just simply means that our final answer will have a y in. Okay, so don't worry about that. We're not going to get a final neat number at the end. We're just going to have a y in our answer. So I'm not concerned about that. So basically, I've been told that y is 2 to the power of x. Okay, so I need to make this relate to 2 to the power of x. So let's treat them both separately first of all. Let's focus on first of all the 2 to the power of x plus 1. So let's call this a and b. So 2 to the power of x plus 2. Okay, I need to make that look as much as possible like 2 to the power of x. Okay, well, have a look. I know a law of indices, but I can use it in reverse to deal with this. So 2 to the power of x plus 2. Well, what can you think of a law of indices which happens when I add the two powers together? It's when I have the same base and I'm multiplying. So in other words, if I had 2 to the power of x times by 2 to the power of 2, would you be happy that that would give me 2 to the power of x plus 2? Because that just tells me if I'm multiplying two bases together, okay, so two numbers with the same base together, that means that I should just add the powers. Okay, so I've just literally used the first law of indices in reverse. Okay, in reverse. So now, because I can write 2 to the power of x as y, okay, because I've been told y is just 2 to the power of x, and because I've got 2 to the power of x there, okay, I can write that as y, and I'm going to multiply that by 2 to the power of 2. Well, 2 to the power of 2 is just 4, okay? So instead of writing y times 4, I'm going to use my algebra notation and just write that as 4y instead, okay? So that's all this question was asking. It says, well, look, I'm going to tell you that 2 to the power of x is y. Can you rewrite 2 to the power of x plus y? Instead of any x's in your answer, I just want to have purely y's in my answer. So you notice that I'm just using laws of indices kind of in reverse here to just get an answer purely in terms of y. So you notice my answer has a y in and no x's, okay? Let's try 4 to the power of x. Let's try the next one, okay? 4 to the power of x. So let's have a think. Well, okay, I need to make this look as much as possible like 2 to the power of x, because I know that's y, all right? So, okay, can you think, well, I see a 2 to the power of something hiding in here, don't you? Because look, 4 is just 2 to the power of 2. So actually I could rewrite this as 2 to the power of 2. Could rewrite this as 2 to the power of 2 all raised to the power of x. Do you notice that? Yeah, 2 to the power of 2 is just 4. So I've literally just rewritten it as 2 to the power of 2 all raised to the power of x. Okay. Now because I know that I'm just going to be multiplying these two things together, so 2 to the power of 2 multiplied by x, so 2 to the power of 2x, okay? Just going to multiply the two powers together by my third laws of indices, okay? And actually in this case, it doesn't matter what order I multiply them in, okay? So I could multiply it as 2 to the power of x times 2 instead of 2 times x, okay? Or I could actually go backwards and write this as 2 to the power of x all raised to the power of 2. Just stop and pause for a second. Are you happy that if I go backwards, so 2 to the power of x, all raised to the power of 2, I should get 2 to the power of x times 2? Okay, so I've just kind of used my laws of indices in reverse here. All right, so therefore, because I know that 2 to the power of x was just equal to y, okay, then in which case I will just end up with y to the power of 2. So 4 to the power of x could be rewritten as y to the power of 2. So I'm just kind of showing you the types of I guess, acrobatics which you could do with the laws of indices. So once you get these laws of indices in your head, right, you can do all sorts of fancy acrobatics, okay? Really what I've done with this kind of last few questions, okay, particularly this last one, is I've just used the laws of indices, but instead of using it the traditional way, instead of thinking, I know that 3 to the power of 3 to the power of 5 times by 3 to the power of 4 should be equal to 3 to the power of 5 plus 4. So in other words, instead of starting on the left-hand side and moving to the right-hand side, simplifying to the right-hand side, okay, in this case, I've gone the other way. I've realised that if I have a base with two things being added together, I can separate that up into two individual bases with two individual powers, okay, being multiplied together, right? So it's just really knowing these laws of indices and being able to work with them both ways, okay? Now, just as one final example then, okay, now this example I want you to have a go at for homework, okay? So let's just give you a question, that's not example, question. And this is a question I want you to have a go at for homework. If you have any issues, then please bring it along to your next lesson with your teacher, okay? But can you try to simplify it for me? In fact, no, I'll call it a solve question. Can you solve this for me, okay? So 3 to the power of x multiplied by 9 to the power of x plus 2, all divided by the xth root of 27, okay, equals, let's say that's equal to 81, okay? So can you have a go at solving this for homework for me? Okay, so it's a simple, it's just basically using your laws of indices, which we've just gone through, okay? A little bit more involved example, but effectively you want to end up with, just a hint, you want to end up with x equals. So to start off by using your laws of indices, simplify the left-hand side as much as you possibly can, okay? And then see what you can do from there. If you have any issues with this, then please bring it along to your next lesson and your teacher will go through it with you, okay?